And yeah, so I'm going to talk about this work I've done with Adam Levine and Arvind Shahbazi Mogaddam, who are both postdocs. Arvind used to be a grad student, but as of yesterday, he's a postdoc, I think, or today. And yeah, so this is a TIFR talk. If you go to the top, this in options, there's a thing called annotate. Use it freely. You can like write on my slides to ask questions and stuff. Yeah, and like yeah.
Although, as you know, we are more likely just to interrupt you. Sorry.
Yeah, sure, but like yeah, you know. Great. So what am I going to talk about? Okay, this is not okay. There it is. Just to remind everyone, I'm going to talk about like something in ADS-CFT, which is a duality between a higher dimensional gravitational theory called the bulk and a lower dimensional conformal field theory called the boundary. And in the UV, you know, people believe it's an exact duality between a quantum theory of gravity and a UV complete CFT. That's not what we are going to do. We are going to like talk about an IR version of the duality, where it's just classical gravity and bulk effective theory in the bulk, and you know the effective low energy part of the CFT in the boundary. And really, a lot of interesting stuff happens just in the IR and the way stuff gets encoded into the IR. And roughly the program this problem and this talk is a part of is called bulk reconstruction. Bulk reconstruction is a program of writing bulk effective theory operators as boundary operators. Okay, there is the basic version of bulk reconstruction is called the causal wedge reconstruction, where basically you reconstruct a bulk operator on a region of the boundary which is causally related, and this just uses equations of motion. Okay, and this is it's actually pretty hard to do it explicitly beyond simple cases, but people more or less believe it can be done. Okay, but the somehow more interesting for us is something called the entanglement wedge reconstruction.
Sorry, Ronak, sorry to interrupt you.
Sure.
It's hard to do. You just use the standard kernel and so on. Can't you construct it for any supergravity field at least?
Right. So the belief is that it should work for a fairly large class of geometries. And in most of those cases, you can't actually solve the Klein-Gordon equations. And it should also work for interacting field theories. And like, yeah, so it's exactly. In very basic examples, like, you know, stationary black holes or vacuum ADS is known, but beyond that.
Okay.
Yeah.
Thank you.
Right. Yeah. So what we are interested in is entanglement wedge reconstruction. The entanglement wedge is like a bigger region associated to a boundary region, and it contains a causal shadow, something that's not causally related to the boundary at all. And well, the way to do it is entanglement. It's in the name. There are like there are at least two explicit algorithms, but getting those algorithms to do anything is very hard, and like they are only useful in very simple cases. Okay.
And sorry to interrupt again, but you'll give a precise definition of entanglement wedge, I assume, as we go along.
Yeah. Yes. Sorry. This is like just yeah.
Sure.
Yeah, and for V1, is this the same as, I mean, ignoring loops, is it the same as asking, given the boundary values of fields, what is the bulk value?
Yeah, it's a related question.
Is it related? Same question.
Given the boundary values, yeah, basically it's like given boundary correlation functions, is there a kernel that relates it to bulk correlation functions?
But isn't it just a classical question of, given the normalizable part of the fields at the boundary, what is the field at the bulk? Just a classical question or not?
It's more than classical field theory. Like, yes, the basic version, which is free fields in free fields, is classical, but that's because free fields are basically classical. you can go beyond that to interaction to the.
Suppose I look at interactions but ignore loops. Then isn't it still this classical question, including classical interactions, or not?
Yeah, I assume. Yeah.
Okay.
Probably, I guess.
Okay. Thank you. Yes.
Yeah. Sorry, I haven't thought about it in this language. Right.
So Ronak, just one more thing. So for interacting theories in perturbation theory, under some follow-up papers of HKLL, maybe by some HK, the same combination or some other papers, where they introduce nonlinear terms in the HKLL construction itself.
Yes.
So for example, the bulk field is some kernel times the boundary value. Then some other kernel with quadratic terms in the boundary operator,
Right.
and things like that. And but that's not the last word.
That is not even clear. No, it is not, because you can you have to do it theory by theory, and I think my memory is that the interacting stuff, they had worked it out for all of ADS, but if you want subregions of ADS, I'm not sure if they worked it out as explicitly. Like I don't know if they could just even at the free level, just when you look at subregions of ADS, there were problems with the way they did it.
Nice.
They were later solved by Sorath and so on, and at the free level. But so I'm not. I haven't reminded myself of what the current technology for explicit stuff is. Sorry.
Okay.
Yeah.
Sorry, Ronak, I just to get the setting clear. Suppose we have global ADS and we take a patch of it of length, I think, length in the time direction 2 pi and going all around global ADS. Okay. What your causal wedge of this would be some part of the inside of global ADS, but from the field theory, it's sort of clear that this data would be enough to at least in perturbation theory would be enough to reproduce all of the field theory data.
Yeah.
So it's clear that you should reproduce all of the bulk.
Yeah. The reason for that, Shiraz, is that the region you described in the boundary, its causal wedge is all of the bulk.
It's all of the bulk. I see.
Yeah. You have to restrict the boundary region to get smaller causal wedges.
I see. Thank you.
Yeah.
Yeah.
Sure.
So just to understand, I was also going to say that in that case, if you take 2 pi, you get the whole bulk, right?
Yeah.
Okay. Yeah. All right. Go ahead.
Okay, good. So today, what I'm going to say is that I'm going to show you that there are certain cases, and a fairly generic class of cases, where doing a causal unitary and letting it back react via gravity allows you to see this causal shadow region. Okay. That is like the one-line summary of my talk. And then I will tell you about what the causal unitary is, and I will show you why the gravitational backreaction is enough. Yeah. So just to give you an idea, I use this word seeing here. What is seeing? Seeing means that there is some causal relationship between two operators. If one operator is to the past of the other, we say that the future operator can see the past operator. Okay. And so there are two actually examples of seeing in the literature. Okay.
Sorry to interrupt you again, Ronak. Is that the same as saying that in general the commutator then of the two operators, one in the past of the other, won't be zero?
Exactly. It's non-zero commutators. That's right. That's completely right.
Okay. Thank you.
Yeah. Good. So one way of seeing is called the Gauss-Jeffreys wall construction, where basically if you have, say, an entangled pair of black holes, you can use some of the entanglement to throw in negative energy shocks. And negative energy shocks, as I will expand later, actually allow you to see behind the horizon. they cause what are called time advances. You can see that this red line is coming out before it went in. Okay. So this allows you to see behind the horizon. Another example is ADS Vedya. In ADS Vedya, so this red shock is the Vedya shock. It's the one that's increasing the size of the black hole. And it turns out that if you boost the shock, okay, the amount of time delay, because this is a positive energy shock, so it was a time delay. And so this signal earlier ended up in the singularity, but you boosted the shock and then now it ends up on the boundary. And these are both ways of seeing behind the horizon. Okay. Now,
sorry. The second example, I'm embarrassed to say I don't know. What does that mean? It's when you boost the shock, it's still positive energy, as far as all the energy conditions are concerned. Oh, and the shock to begin with was going to come out. It just comes out with a little bit of a delay, but it can still come out. That's what you're saying. Okay.
Exactly.
I got it. Okay. Yes.
Yeah.
Okay.
And I will expand. I don't expect the people who are not familiar with this to understand this. I will talk more. There's an entire section devoted to these two examples.
Okay.
But the point is that much like a bifocal, these are two completely different ways of seeing. What do you say? This talk uses this thing called Cocycle flow, which does both at the same time. And exactly in a very precise sense, it does both at the same time. Good. So anyway, this is the plan. I'm going to give 4 introductions, and then the way I introduce will.
No question.
Yeah.
Bhaiya, I just wanted to know, suppose something related to Surat sir's proposal. Suppose we send in a shock wave in your protocol, is it that we can instantly get the information at the boundary, or we need to wait for causal time?
Yeah, I mean, I'm not sure what you mean by instantly, but yeah, nothing apart from at the shock, nothing propagates acausally.
Okay, thank you.
Yeah. Sorry, did that answer your question? I'm not sure I understood it.
Wanted to, there is a discussion about retaining all of the data using holography instantly. So
Right.
I don't know whether, I just wanted to know your viewpoint regarding the same.
Oh yeah, no, nothing I say is it's like the way I do things is completely complementary to that approach. Yeah, it's neither in contradiction with neither in contradiction with anything in that paper, nor I think does it confirm anything he says.
Can I follow up a similar question?
Yeah.
Why is it? Meaning, I just wanted to get some more clarification about it's not in contradiction, or neither does it support the idea.
Mm-hmm. So what do you mean?
I'm sorry if I'm getting tangential. Maybe we can. It's up.
No, please go on.
Okay, thank you. So suppose, okay, so you were mentioning that your approach is complementary and something different, and it does neither supports nor accepts the given proposal. So we will be getting some more clarification as to what you meant in the talk.
Not really. I wasn't going to mention that stuff, but I can just quickly say it. So there are 2 important things. The Surat's papers with like Alok and the recent one also, they talk about reconstruction and detection of stuff in the boundary or in the bulk. Okay. Yeah. And that uses a specific projector, which from my point of view would be very complicated. Okay.
Okay. Yeah.
And so now, I am not allowing they make sure that they always work with all of the boundaries. I will always restrict my boundary region. And B, I don't I don't have the same, like my boundary observer doesn't have the same technology. I think that that one has.
Yeah. So if we change the technology, can we measure the information holographically instantly?
Like I have no reason to disbelieve his paper, which says yes.
Thank you.
Yeah. But yeah, it's just that I have nothing to say about that. And is it okay? Are you okay? Is that okay? Like, do you want some more details?
I'm fine. Thanks a lot.
Yeah, sure. Yeah. The point of flashing these two things is that people who are familiar with these ideas will recognize them pretty quickly. And the conclusion of my talk will be that this Cocycle flow does both at the same time. Okay. And now this is the plan. I'm going to give 4 introductions, and then the actual result section will be, they will be very biased introductions, so that the result section will be almost immediate. Okay. This is, yeah. So first, let's talk a bit about ADS-CFT. In ADS-CFT, as I mentioned, we are thinking about an IR theory in the bulk. Okay. In the IR theory, there's a semi-classical expansion. So the bulk is an asymptotically ADS-D+1 spacetime, and we are working in the limit where Newton's constant is really tiny. So the semi-classical expansion is writing the metric as some background metric plus root g Newton into the graviton part plus g Newton into this h1 thing plus blah 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 blah, all orders. So the action looks like Einstein, Hilbert, I forgot a cosmological constant piece, forgive me, plus a matter action, where there's some matter field in the bulk.
I'm sorry, I'm interrupting again.
Yeah, sure.
Why is it that in semi-classical expansion we are only considering order G Newton effects? Meaning, how do we know it's a semi-classical expansion?
How do we know semi-classical? Because basically because if you okay, we're good. So you can actually let me write it this way. So Einstein's equations, okay, look like R equals G Newton T, right? I'm being very schematic here. Now, this when there's a quantum field theory in the bulk, this guy has fluctuations. Okay, so the fluctuations in the metric are going to be controlled by the same number G Newton. So at leading order, whatever the QFT is doing, the gravity sector doesn't care about it. So you can treat it completely classically. And then also another way to say it is that the G Newton acts like H bar. If you look at, if you remember quantum mechanics 1, there was a 1 by H bar in front of the action, which controlled the quantum expansion. Maybe that's a better way to say it. I'm sorry. Yeah.
Thank you very much.
Yeah, sure. Good. So this H half guy so we are going to work at the order where the action looks like this. Okay. This H half guy is just some spin 2 field, completely free. And basically the equations of motion are going to set H1 to some function, some integral kernel into the stress tensor. Okay, the matter stress tensor. Good. And this H1 doesn't have any dynamics at this order. It's just kind of keeping track of the backreaction. Okay, and we will throughout this talk take states where this H of expectation value is 0. I actually don't know how to deal with non-trivial expectation values of H of. And we will take the matter QFT phi to have a lot of degrees of freedom. C is much greater than 1. C is the degrees of freedom. But the number of degrees of freedom is still much smaller than 1 over the Planck number. Okay. Nothing makes dimensional sense because I set L equals 1, the ADS radius. So, put factors of L.
Can I ask another question? I'm very sorry.
Yeah, sure.
Why is it that we need a large central charge in the theory?
It's because I put it in because I like it.
Okay.
Yeah. Basically, what's going to happen is that if you don't have a large central charge, right? So suppose you have, let me draw something. So suppose you have two regions, two null lines, and these guys are, what do you say? Maybe I should say it properly, maybe better, sorry. Suppose you have a null line, and what happens is that the stress tensor splits the null line. Okay, so this is happening because of backreaction. So there's two states. In one state, the null line goes to the left one. In the other state, the null line goes to the right one. Okay, I'm trying null lines on two different geometries together. Yeah. So what does that mean? That means that this distance, the separation, looks roughly like G Newton into the expectation value of the stress tensor, rather the difference in the expectation values, right? And now, suppose I want to send a signal through this. Suppose I want to send a signal through this gap. Okay. If the expectation value of the stress tensor is 1, the signal also has stress tensor equal to 1. Okay. I'm just counting powers of C and G Newton here. And the backreaction is going to close the gap. Okay. So there's no way to send a signal through gaps of order G Newton. So this C is helping you there because what it's saying is that, look, this gap is small in G Newton counting, but still much bigger than G Newton. So you can send a small signal through it. And that is what C is going to do for us. Did that help or would that just confuse you more?
Yeah. Thank
okay,
you.
Thanks. Great. Yeah. Okay, so that's why I have a large C. Thanks for asking that question. I would have brought it up later, but this is actually a good place to bring it up. Yeah. So
Sorry.
H1 has no dynamo.
Sorry, Ronak, I have a, what exactly is C? What
C is the number of degrees. It's roughly speaking the number of degrees of freedom of the QFT. If it's a 2D CFT, it's a central charge, but basically says
bulk or QFT on the boundary, or what is going on?
Oh, this is a bulk QFT. This is entirely a bulk story here.
So you may have mentioned. So the setting is you have gravity plus matter, and C is the matter setting.
Yeah. It's a surprising fact that, to my knowledge, like the first time someone used this setup was recently with the whole black hole evaporation story. But it's actually really useful for a bunch of things where you take this limit. Okay. Okay. And the other thing I want to tell you about about ADS CFT is the extrapolate dictionary. As all of you know, when we say it's an ADS space, we actually mean it's an asymptotically ADS space. And asymptotically ADS spaces have a conformal boundary where we can say the CFT lives. And what do you say? If you have a CFT living on a metric of this form, the vacuum state dual to it has a metric like this. And the point is that every state will have a metric that looks like this plus order z bar 0 terms. This is a different expansion than the previous slide. This is a near boundary expansion. This is true even for like extremely high energy states. Okay. And the extrapolate dictionary is a bunch of operator relationships between bulk effective theory fields and simple boundary operators. And what you do is you take these bulk effective theory fields, you strip away a conformal factor because the boundary of ADS has infinite size, but CFT lives on a finite size manifold. So these conformal factors make sure that you're on a finite size manifold, and then they become the CFT operators. And this is the extrapolate dictionary, and this is used for all bulk reconstruction. You usually try to rewrite a bulk operator as a near boundary operator, and then use the extrapolate dictionary. That is the game. So that is the two things I wanted to remind you about ADS-CFT. So the second introduction, it's about wedges. What are these wedges? What is the reconstruction business? Introduction. Yeah. So first, let me tell you about what a subregion of a QFT means. A subregion of a QFT is given by a
maybe I should have asked in the previous slide. So if you go back to this extrapolate thing, yeah. So here, let's take the last couple of equations.
Yeah.
What is the idea that so T mu nu is an operator, and this H half mu nu is also an operator in the respective Hilbert spaces.
Exactly.
And okay, so you say, and then there is supposed to be dot 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 on the right hand side of T mu nu, in the sense that this is only reconstruction very near the boundary.
Yeah.
And so this is just the expansion of the kernel, right? Or not?
It's sure, but the kernels are built based on this dictionary. This is like the starting point for all such things.
So, well, I mean, so it's just the GKPW construct.
No, it's not, because these are normalizable modes. These are not sources; these are operators. This is just like a.
Oh, so I see. Yes. So this is a normalizable equivalent of the GKPW.
Yeah, exactly.
It's called the extrapolate dictionary. I see.
Yeah.
I mean, in the sense that this is what Sandeep and company did.
Exactly.
Okay.
Yes. So, okay. The second introduction is to these wedges and this reconstruction. Sandeep, did you want to ask a question, or did you just turn on the video? Okay.
No, go ahead.
So I just started check. So anyway, so subregions of QFT called causal are like given by causal diamonds. What is a causal diamond? You take a time slice. You take like a bit of the time slice, call it A. Okay, and then you just draw like the light rays from, you draw the obvious light rays, make it look more like a diamond, and then it's called a causal diamond. And the reason subregions of QFTs are given by causal diamonds is that any operator in this causal diamond, by Heisenberg evolving to this time slice, lives within the subregion, within this interval A, right? So basically, it's like the diamond is a causal completion of the interval. Yeah, so this is, I should warn you that if in the higher dimensions, if A is a funny shaped region, this causal diamond looks horrible. It's not a diamond, it's very rarely a diamond. Some people call it a domain of development. Cool. And so that is what a subregion looks like, and we should always be thinking about causal diamonds. So given a causal diamond, it has a bunch of operators on it, and the reduced density matrix is defined as a matrix, okay, which gives the right expectation values on the Hilbert space of the subregion. Okay, so this is the psi is the global state. The reduced density matrix is defined by this equation, and the entanglement entropy is the von Neumann entropy of that reduced density matrix. I should tell you that in QFT, this reduced density matrix is a bad operator, and this entanglement entropy is a divergent quantity. But there's a lot of stuff you can do with it still. Okay. Now, so
the reduced density matrix is the smallest density matrix that reproduces all expectation values.
So basically, it lives on the Hilbert space. It basically lives within the algebra of the subregion. So you can write it in terms of other operators in the causal diamond.
Yes.
On that products.
Right. Of course. I mean, if you just said that it was the density matrix, it could be the density matrix of the full state of the full Hilbert space. Right? You want to
exactly. Yeah.
Yes.
Yeah.
Thank you.
In other words, I didn't define what this trace is over. And like once you define what the trace is over, that is also fixed. But yes,
No, but sorry, Ronak, I think the trace is the underlying trace in the set of all operators in the beginning Hilbert space. No, it's what you said, that the density matrix has to be built out of the algebra of operators defined in the causal diamond, right?
yeah.
That's
So
the smallest possible, I think.
okay. Right, I agree. I think, Sandeep, we are having a semantic issue where I'm talking about this guy and you're talking about this guy. So if you talk about this guy, it lives on the Hilbert space of the subregion. This guy lives on the Hilbert space of the full thing. These are A and A prime. A prime is the complement. Yeah, it is a completely semantic issue. Yeah.
Okay, fine. I'm sorry about that. But I mean, at root, shorn of semantics, I mean, Shiraz's point is true, but taken care of by the fact that you need to build the density matrix out of the algebra, subalgebra in the region of interest, right? Roughly.
Yeah.
Okay.
Yeah, totally.
Fine. Right.
Cool. Okay. And in ADS CFT, the entanglement entropy is given by the beautiful Hubeni-Ragumani-Takayagi formula, which was built up over a bunch of papers, which says the following: given a boundary region A, okay, find the set of all surfaces which extremize this quantity called the generalized entropy, the area plus the bulk entanglement between A and the surface. Okay, find all of them and take the one with minimum generalized entropy. And here are some examples, like if you have a region like this, I picked up all these examples from this paper here because I'm too lazy to make my own pictures here. So for example, in a black hole, the HRT surface is the black hole horizon. In the case when there are two regions, in the case when the region A has two components, A and B, sorry about the nomenclature, there's two candidates. One candidate goes like this and one candidate goes like this, and always you pick the one with minimal generalized entropy. Okay, and there's something called the homology constraint, which I kept it in for technical correctness, but I won't go into it. The homology constraint makes sure that you can tell the difference between high energy black holes and high energy black hole pure states and reduced density, thermal density matrices. Okay. Now,
can I ask another question?
Yeah.
Why is it that we need to extremize the generalized entropy to get the entanglement entropy of region A? Naively, we would have expected using ADS CFT dictionary that the information about the entanglement, information about some region A should be in the causal wedge. So why is it that we are extremizing the area? And even if I agree with the Ryu-Takanagi formula, why is it that we need to generalize it for HRT surfaces? We need to consider the minimum of all such co-dimension two surfaces to get the entanglement entropy of region.
So you asked a bunch of questions.
Meaning I'm just confused with the. I'm just yeah.
Okay, I can
I just had a.
Sorry, what?
Yeah, I'm sorry I interrupted in the middle. I just wanted to know why is it the minimum of all extremal surfaces? Even if I get some intuition for why we need extremum using Ryu-Takanagi formula, why is it that we need minimum of all co-dimension two surfaces to get the entanglement entropy in the HRT formula?
Good. The short answer is the kind of unilluminating answer is that there is a calculation where you get this formula from a path integral. So you basically have a path integral with two saddle points, two classical saddle points, and then you have to, and the point is that, whenever you write a path signature as a saddle point, you get e power minus s1, where s here is the action, that's e power minus s2. And which, if s2 is bigger than s1, this term is, the second term is exponentially smaller. So you end up with the minimum to leading order. And
so this, yeah, I'm sorry.
yeah, so this is the unilluminating answer. The illuminating answer would talk about two papers from last week by Faulkner and by Pennington and Akers, which I haven't managed to read in detail, but they give an explanation for why this minimization turns up. But in practice, what happens is that if you try to prove this formula, you find that there's two classical solutions to your path integral, and you need to pick the one with lowest action, and the one with lowest action is the one with minimal generalized entropy.
So is it that it's an approximate formula where some non-perturbative corrections, if possible, can change the formula?
Yeah, exactly. That's not even non-perturbative. You can. So first of all, it's approximate in the sense that this works to an arbitrary order in G Newton, but but an arbitrary but finite order in G Newton. Okay. And second of all, you can mess with it. The Akers and Pennington paper actually found ways to mess with it just at leading order, like you make it fail at leading order.
So is it that if I consider order G Newton effect, then this formula is always valid? For any,
there are some subtleties with like gravitons, but yeah, modulo those, yes.
Okay. Yeah.
And oh yeah, one more interesting question you asked is why we need the HRT formula. The HRT formula is the fact that it's an extremal, not a minimum, and the answer to that is pretty nice. That basically you can always minimize an area arbitrarily by wiggling a surface in a time direction, because if you make a very wiggly surface, most of it is time-like, and so the area is very small. So you need to actually maximize it in the time direction and minimize it in the space direction, and so it needs to be an extremum. It's like a saddle point. Yeah. Is that it, or?
Yeah. Thank you. I will think a bit more about it.
Yeah. Yeah. There's a lot of work on this right now. Mm-hmm.
Thank you.
Yeah, sure. Cool.
Could I ask should I think of this as first two terms in an infinite series? And if so, is this formula still valid when S bulk, when the second term is of the same order of magnitude as the first term?
Good. So you should think of this as the first n term. So S bulk can like have corrections. You can just keep on adding corrections to this, and it basically first n terms in an infinite series. And by the time in practice, it's very hard to make S bulk compete. Sorry, like configurations where S bulk itself is 1 by G Newton usually have large amounts of backreaction, and like you're basically in the wrong classical solution, because you need to be looking at this in the actual solution plus perturbations. But there are times when in the extremization, even though S bulk itself is small, it plays a non-trivial role in the extremization, and this gives you the pH curve, as you probably know. So like this actually plays a huge role in some cases. But in practice, I don't know any case where S bulk itself competes with the 1 by 4G.
I see. Thanks. So S bulk is not an order 1 fraction of the other term in these page curve discussions? No, only the derivatives are. Okay. So what happens is that there are derivatives where basically because of some metric factors, S bulk derivatives are extremely enhanced. Okay. Thank you. Yeah.
So Ronak, maybe a related question. Suppose you didn't take the central charge to be much bigger than 1, then S bulk would, so right now the two terms are like, one of them is of order n, the first term, that is the 1 over G Newton, and the other one is order C.
Yes.
So now imagine that you are working with C of order 1. Then the question that Shiraz is asking will be even more acute, because the you know, like the graviton contribution at the moment would be of order 1. On the other hand, the bulk matter contribution is of order C. So there is some point in ignoring the graviton contribution, but keeping the bulk matter contribution, because the bulk matter has C. But
exactly.
But if C is also of order 1, then of course, you know, you have to at least include the graviton contribution, or maybe that is already understood that there is a graviton contribution and so on.
So I will just say that everyone in this discussion, like, it's conventional to ignore the graviton contribution because people don't know the right language to incorporate it.
Then C much greater than 1 becomes imperative.
Yeah, it's like that is when everything is best understood. Yeah.
Just briefly, you should go on, but is the issue that computing or defining the entanglement entropy for the graviton isn't well enough understood? At least for gauge theories, it's well enough understood, but not.
No, actually, the issue is like, that is one issue, but what do you say? People understand entanglement entropy for gravitons like not too shabbily now, based on some work by Causally and Takayanagi. But the issue is again like how to define the surface with the graviton contribution. I never completely understood the set of issues. I'm sorry. But like, it's just somehow the language for incorporating this, even if you can deal with spin 2 fields, is a bit confusing.
Okay.
And yeah, I'm not the right person to ask. I'm sorry.
No, that's fine.
Yeah. Cool. Okay. So now the point is that I'm going to forget. I just want to focus in on this extremization, which is a completely local procedure. You're locally wiggling the surface and checking this is functional. And because it's a local procedure, there's a local differential equation that you need to solve. Then basically, when you extremize, you need to wiggle. You might think you need to wiggle in any given direction, but there is a vector space structure in directions. It's called vector space. That's how vector spaces are thought of. So you just need to pick a basis. So we pick a null basis. That is standard. And in null basis, basically you have to make this functional to vanish. The square root of h is the induced metric. H is the induced metric on the surface. Square root of h is root g. And the reason I put the fancy 1 by root h is that this guy here is called the expansion. It is the change in the area per unit area. Root of h is the unit area, and this is the change in the area. Okay, and so this guy, this combination is called the quantum expansion. Yeah, so this is what it looks like to wiggle a surface. And the point is that it's a completely local equation. And this is what we will use. Cool. So now let's define some vectors.
Can I ask a question?
Yeah.
Why is it that we are considering expansion only along null hypersurface? Sorry.
It is a null direction. Null vectors form a basis for the transverse Hilbert space. So the point is that I should do some. Yeah. Is it clear that this surface is codimension 2? There are 2 transverse directions.
Yeah.
There's time and there's like the one you see in all these examples. And so it's just that you need to pick some basis, and this is a very convenient basis.
How do we know here that it's a null hypersurface? I'm very sorry for that.
It's not a null hypersurface. What you need to do is you need to.
Okay, yeah. I got it. Okay.
Yeah.
Okay. It's some basis we are choosing. Okay.
Yeah. Just to complete the sentence in case other people have the same question, the way you should think about it is that the dotted line here is the candidate HRT surface. So what we are doing is we are wiggling it in another direction and then checking the generalized, checking this quantity. So we're subtracting the generalized entropy for this wiggled R and the unwiggled R, and that's a derivative. And that's what we want to have. That's what we need to vanish. Good. Yeah.
Is this some statement also about the extrinsic curvature for this co-dimension 2 surface? Is that it's?
Yeah. I think I think it comes down to the trace of. So if you just want, you forget about the second term.
Yeah.
That I think this is the same as the trace of the extrinsic curvature is vanishing.
I see, but there's a correction to that now. Huh?
Yeah. And yeah.
Okay.
Cool. So let me define some wedges. So we have a boundary region A. Okay, good. Sorry, I should have mentioned this earlier. But now this A is always a causal diamond, but I'm going to look at the CFT from the side. So A is going to just look like a line from time T1 to time T2. And that's what this guy here is. Okay. Okay, good. And now what you can do is you can go to the top of A and draw null lines to the past, go to the bottom, draw null lines to the future, and then they intersect somewhere. Okay. The point at which they intersect is called the causal surface. And everything between the causal surface and A is called the causal wedge. The name should be completely intuitive. And in the language I want to use today, things in the causal wedge are things you can see from both the past and the future. Okay. This is a very annoying way to say it, but here you can see it from the future and also you can see it from the past. Like time reversal is something I'm allowed to do. So that's why I say it like that. Okay. Now, there's also in a generic state, the causal wedge and the entanglement, the causal surface and the HRT surface do not coincide. And there is a theorem saying that the HRT surface is further out than the causal surface. Okay. And the topology, okay, good. And now what you do is you go to the HRT surface and you draw future and past null lines. What you find is that at some point, nearby null lines start intersecting. That's called a caustic, and that's what these points are. Okay, and then you truncate it, like wherever two null lines intersect, like equations of motion fail when null lines intersect. So you can't go beyond that. You need more boundary conditions at these caustics. And so now what you find is that when you look at the place which is actually causally complete in terms of differential equations, both of them have a boundary projection which is this A region. So, okay. And this entanglement wedge can be pretty complicated, but today we will only look at cases when the HRT and causal surfaces have the same topology, like there is a simple region in between them, which we will call the peninsula.
Sorry, Ronak, can I just, I'm sorry, ask you now or after you finish your description? Sorry.
I think I just finished the description of that picture.
Go ahead. Sorry about that.
No, I did finish it.
Okay.
That was the causal wedge entanglement.
Okay. So if I understand, first of all, E of A in a sense is the tip of the Ryutakanagi surface, huh?
No, it's the entire Ryutakanagi surface. I'm sorry, I do the, yeah.
The Ryutakanagi surface goes all the way to the boundary, right?
Yeah, but I'm drawing like a cross section of the whole thing because otherwise I would have to draw, be like, Veronica and Mukund and draw these marvelous pictures on the left. But I'm me, so I draw these cross sections.
this cross section is not the radial direction or something in time, it's something else.
Yeah, it's roughly radial direction and time, but so you should think of it as the following cross section of this picture,
Okay.
right? You should think of it as like whatever you see like this is here.
There are two E of A. There's a capital E of A and curly E of A. I think Sandeep
Yeah.
said curly E of A.
Yeah, the curly E of A is the full arcade surface. So if you look here, if you look here, this blue line goes all the way to the boundary, and it is the HRT surface. And if you just try to, if you think about this cross section here, then it looks like this picture on the right.
Then what is the non-curly E of A?
Non-curly of E of A is the entire wedge. It's where you draw these null lines, stop where things start intersecting, and that entire causally so it is a bulk region that is causally complete.
It's the inside of E of A.
Yeah, you should think of it as inside. Yes.
Sorry, Ronak, I missed two. appears.
Yeah, go ahead, Abhijit, and then I have a follow-up to what I was saying. Go ahead.
Yeah.
No, sorry, this is something that I missed perhaps, but you start these null lines from curly E of A, and then you change this line with the purple line. What exactly happens there at that point?
Okay, sorry. Maybe So what happens is that this is a cross section, right? So there's going to be null lines from here as well, like null lines from sorry. Maybe that was Basically, like, you have to draw null lines from every point on curly E of A.
Okay.
Right. And what happens is that they start intersecting, like at some point.
Okay.
Yeah. So when they intersect is the first point at which they intersect is this corner here. Is this corner here?
At the point you're saying, or some locus?
No. Again, it's a cross section. There's an entire So, for example, let me maybe draw an example of this. So, I'm terrible at drawing this, but suppose the boundary region is 2. Okay, it's 2 guys, and this is the HRT surface. It goes between them. So this is A1, this is A2. Okay, then basically the intersection. So this is a time surface. I'm going to throw the intersection down onto the t equals 0 surface. I'm going to do a projection and draw it in pink, and then the intersection looks like this. It's like the point where they start intersecting looks like this is the surface of intersections. So basically, like, things from here and things from here intersect here, and so like you just have So you have to stop your wedge there.
Okay. Fine.
Yeah.
Ronak, the purple line is a null ray from the caustic to the boundary, or what is it?
No, it is the locus of intersections.
Oh, it's the locus of the caustic intersections, is it?
Yeah.
Thank you.
Like if you go here, like here, basically infinitesimally close null rays are intersecting, but if you go here, finitely far away points null rays are intersecting.
Okay.
Yeah.
Okay. Thank you.
Ronak, I'm going to ask something very stupid, very remedial, but let me ask it. The surface A is a d-dimensional. It's a d-dimensional surface of the boundary, right? If we're doing ADS D+1 and boundary D, surface A is d-dimensional. Now, normally when we compute entanglement entropies, I mean, in a time-independent situation, we compute entanglement entropy of a d-1 dimensional surface, right? It's some region of a space-like slice. So I'm trying to understand the connection between that picture that when we normally compute entanglement entropies of a time-independent surface, and what you're doing here. This
that connection is this. So this is the so now I'll just write the numbers for you. So this guy here is d-1. Okay, and so this is a subregion of a d-1 surface. But then you have to you causally complete it. Okay, and you get a d-dimensional object, a d-dimensional region.
So the object A in your diagram that in the next diagram is the causal completion of some surface?
Yeah.
Not an arbitrary region. It's a causal dimension.
Yeah, exactly. It has to be
Okay.
causally complete. That's completely right. Sorry. I should have been clearer about that.
Okay.
Yeah.
Yeah.
Good. Are there any more? Is this picture clear now?
Can I ask a quick question?
Yeah, sure.
What is small e of a?
Curly E?
Yeah, curly e.
Yeah, okay, good. Sorry, I was just confirming. It is the HRT surface. It is this blue line here.
What does it? Okay. It's the
Yeah,
boundary of the bulk domain. Sorry, it's the boundary of the region which is accessible using HRT prescription.
No, so HRT thing is, so the HRT prescription gives you a codimension 2 surface, right? So if you think about a time slice, it cuts out a specific surface in the time slice. Something like this. This is a time slice. Yeah. So now, if you, now this is a space-time diagram, and if you count it, there's like time and then there's one more codimension here, right? And so this is the HRT surface, and it is the thing whose area gives you the entanglement entropy.
Small e of a is small e of a is curly e of a is the.
Yeah, it's the HRT surface. It's like it is a thing whose area is the entanglement entropy at leading order.
Okay.
Yeah.
Okay.
I'm really sorry to slow you down, but just I get the dimensionalities right. There's the boundary of your diagram here, which is also d-dimensional. But I can't really see it very well, but I think they're purple. The upper bound, the kinky boundary of your diagram, that's also d-dimensional.
This, I believe, if I remember correctly, this is, it has to be d minus 2. No, wait, d minus 1. This has to be d minus 1.
How is it d minus 1?
No, wait, d minus 2, d minus 2, d minus 2. Sorry, this entire bulk is d plus 1.
Yes.
And this guy is going to be codimension 2.
I don't understand how it's codimension 2. I mean, you've got this surface which is d-dimensional. So it's got a d on the boundary. Then there's a d minus 1 dimensional boundary of that. Then it's going out. So it's d-dimensional.
So, okay. No, because, okay, good. Sorry, this is, so basically this A is a diamond shaped region.
Yes.
So it has 4 corners. The top and the bottom are corners. So this corner here is d minus 2 dimensional. Okay, so this CFT is d, the bulk is d plus 1. So this bulk of this guy is d minus 1. So it's just d. Where's the other?
The bulk is
d. Yeah, and now a corner is d minus 2 because it has, it's like it's a boundary of a boundary.
Yeah, right. Sounds good.
So now a line going out from a corner is d minus 1.
Okay, so what I didn't understand is that the line is only going out from the corner, not from the whole boundary.
Yes, I'm sorry. This is a non-trivial factor. Maybe it's some geometrical fact that was proved in this paper here.
Okay, so the HRT surface is emitted from these corners, you're saying?
That's one way to think about it. Usually the way we do it is we talk about, so HRT is d minus 2 or d minus 1. And we say, okay, we define the corners as what you get is as like the caustic from when you throw null signs from the HRT surface. The HRT surface is defined by the minimization procedure. And then the caustic is defined from by drawing null lines. And that is this point here. And then this line is also defined like that.
Okay, thanks.
Yeah.
Ronak, is the entanglement wedge reconstruction known at the same level as HKLL? I mean, in the sense that if you include, say, interactions, cubic interactions.
So good. So entanglement wedge reconstruction, I was just going to get to that. So perhaps Alok, before I answer that question, maybe I'll just stop and ask people if the picture is clear. They know what an entanglement wedge is now. Yeah, thanks. Sorry. Okay, if this is clear, I will just say what the entanglement wedge reconstruction is. So causal wedge reconstruction is a statement that any operator here is an operator on the boundary. Okay, and there are like space-like Green's functions which are known in various cases for this. Entanglement wedge reconstruction is the more non-trivial statement that any operator here is also in this region A. And the reason this is non-trivial is that when you try to evolve it in a space-like direction, don't think too much about what that means right now. You hit these caustics here. Okay, and generically for differential equations, if you have caustics, you need more boundary conditions. But somehow this doesn't matter. You still you can still write this guy here as an operator on A. This is the statement of entanglement wedge reconstruction. In causal wedge case, we know it fairly explicitly in a bunch of cases as Green's functions or as kernels or so on, or as mode sums. In entanglement wedge reconstruction, this proof is entirely abstract. Okay. Basically the way it works is that you show that if a state is clear all drawings. Okay, good. So basically the way it works is that if you have one state where there's an excitation here, and you have a second state where there's an excitation here, you show that. So this is obviously if you're in the bulk, you can only distinguish them if you have access to this peninsular region. Okay, right? Because they only differ in the peninsular region. Mm-hmm. But in the boundary, it turns out that you can prove fairly abstractly that they are completely distinguishable from here, which means that this information of where the excitation is there in the boundary, and it's very abstract. And this is known explicitly only in two-dimensional cases, to my knowledge.
But sorry, you say it's very abstract, but ultimately it's some statement about differential equations which hit caustics, right?
No, but the point is that those differential equations are useless for entanglement wedge reconstruction because they hit caustics and you need boundary conditions there. Okay. I spent some.
Sorry, go ahead. How is the proof given? It may be abstract, but how is it given? Does it use entanglement properties on the boundary or what? I mean.
Yeah. Basically, it uses a measure of distinguishability called the relative entropy. I will define it later. And it says that the relative entropy on the boundary is the same as the bulk relative entropy on this entire region. Okay. And the point is that the relative entropy vanishes only if the states are indistinguishable. Okay. And so in these two states, sorry, I'll just finish my sentence.
I'm sorry.
Yeah. Give me a minute.
I'm sorry.
In these two states, the relative entropy in the bulk is clearly non-zero in the full entanglement wedge. It is zero in the causal wedge, but you can show that it's non-zero in the boundary. Therefore, this information is encoded in the boundary, and generically it's encoded in a complicated way. You need factors of the modular of the reduced density matrix to see the reconstruction. Anything, Alok? Have I answered your question yet?
Yeah, actually, Ronak, for the interacting case, I mean, HKLL I thought demands more, right? In the sense that, I mean, related to what Gautam was saying, that you really require that the operators are microcausal in the bulk, and that gives you these corrected terms in the bulk reconstruction.
Right.
So how do you know that this abstract proof will also ensure that the bulk operators you construct are, causal? I mean, especially if you have.
We don't know.
I see.
Like so you can only check in like a vanishingly small set of examples. Like there are two-dimensional examples and related three-dimensional examples. I think the best one is in this paper from November by Pennington, Schenker, Stanford, and Yang. which itself is, and also there's Cocycle and Maldacena have some examples. I believe these are the only explicit ones.
But
Right
is it
now.
only for free fields, or I mean,
It's pretty agnostic to the type of QFT in the bulk.
okay. Unlike
But we
HTML.
can, yeah. But Cocycle Maldacena, for example, you can check that it's causal in the bulk because the way it's done is very nice and causal. And yeah, but it's in general we don't know, except like we know abstractly that these operators are preserved and the correlation functions are preserved. So yeah, there's no, like, it's not explicit.
Thank you.
Sorry, Ronak.
Yeah,
Sorry. Classically, if I knew the expectation values of operators on the boundary A region, that determines the bulk, the classical that determines the classical solutions of the bulk only inside your causal wedge, right?
Exactly.
So you could have two different classical solutions in the in your peninsular region, both of which are consistent with the same boundary expectation values classically. So this entanglement wedge is somehow inherently quantum mechanical, in the sense that there's no classical analog of it.
Exactly.
Thank you.
Yeah. And that's why, and you should of course go on, Ronak, but that's why I'm trying to understand what this abstract argument is. Is it based on an assumption that the relative entropy in the bulk in the peninsular region, which will be captured in A? If so, of course, we would understand. Anyway, you should go on, but there isn't even an analog of Ryu Takanagi for relative entropy in a precise way, is there? Or am I just revealing?
So good. For extremely close by states, so these two states have the same, these two states, one with the pink excitation, one with the orange excitation, they have like extremely close by, they have the same classical solution or very close by classical solutions, right? For the metric. And in that case, in cases like this, these people proved that they proved using the Ryu Takanagi formula that bulk relative entropy is boundary relative entropy.
I see.
So yeah, and so it's like an RT formula.
I see.
Yeah.
Okay. Thank you. Thank you. Go ahead.
All of global ADS, just a spatial slice of global ADS and a little epsilon width of that in time. The causal there would be very small.
Exactly.
Very small. But we know from field theory that we expect that to give the information of everything. And so presumably that the entanglement wedge is everything?
Yep.
Okay. So one example of this difference between the causal wedge and the entanglement wedge is simply that all of the information lives at one time in the field theory and on the boundary. Whereas the causal wedge for that is vanishing. Is this right?
Exactly.
Okay, is the entanglement wedge there everything? Oh, if you take the entire boundary region.
Entire boundary with very small time.
Yeah.
The causal wedge would still be very small. But the entanglement, I mean, all of the information should be on a given time slice in the field theory. So presumably the entanglement wedge is everything.
Yeah.
But the entanglement wedge is not the causal wedge is obviously a semi-classical notion because you use the light cones of the background geometry. But the entanglement wedge is not a semi-classical notion.
It is a semi-classical notion, right? It's basically saying that you're minimizing this semi-classical object, the area plus S bulk.
That's right. That's what I thought. And in Shiraz's example, if you actually do it that way, you get all of ADS?
Yeah, basically, because if you take all of ADS, area plus S bulk is 0. It's like a pure state, right? So we know its entanglement is 0. So like the HRT surface is the empty set. So basically, basically everything is between the HRT surface and the boundary.
I see.
Yeah.
Okay.
I mean, you can take his picture and just extend the boundaries of the causal wedge around the back side of the cylinder.
Yeah.
And basically this surface curly E shrinks to 0.
Yeah,
You're right. You're right.
that's completely right. Thanks.
Thank you. Thanks, Amit. Yeah. Okay.
But I had a question. So so it sounds like what you're saying is that if I think about observables on the boundary, that there are local observables that measure things in the causal wedge. And then it sounds like you're saying that there are additional operators in the theory that in some sense there's a large commutant of that. So if I look at all of the sort of operators that measure bulk fields that propagate causally to the boundary, those are measured by local operators on the boundary. And it's like you're saying there's some enormous commutant of that operator algebra, which measures things in the region between C of A and curly E of A. Is that a way of saying what's going on?
Something like that, yeah. So what happens is that, let's take Shiraz's example. It's a great example where basically, you're taking a band region in ADS. Okay, that's a band region. And now the causal wedge, as Shiraz said, is like some thing like this. Okay, and now what happens is that clearly you take the operators on any time slice, right? Say and basically you take sums and products of those give you every CFT operator. This is like in n equals 4, it would be the statement that sums and products of single trace operators is all operators, like everything turns up in the OP, right? However, what happens is that an operator here, which is reconstructible on a huge thing, has commutator with an operator localized in the band, but that commutator is suppressed in powers of G Newton or n, or 1 by n, sorry. Like if the commutator goes like 1 by n squared, then at classical level, semi-classical level, that commutator is 0. Okay, and so you have space for these complicated operators, these other operators to live beyond the causal wedge. So in the CFT, the commutator is just non-zero because like literally every operator is there in the band, because you can just Heisenberg evolve any operator into a band. But because that Heisenberg evolved operator is some very complicated guy which almost commutes at leading order in 1 by n with simple operators in the time band, and that is the reason there is space for this. And so it's not a real algebra is the point. It's like some sort of approximate algebra. If you look at, I think Subrat wrote a paper where he's like, where he refused to treat it as an algebra. He's like, okay, let's treat it not as an algebra at all, see what we can do.
Yeah, but I think this gets at an issue which lots of the questions have been circling around, which is that it sounds like to measure things that are in the region beyond the causal wedge, that you would need to use some sense heavy operators on the boundary.
Yes.
Right, and so the sorts of things that Subrat talks about are needing to use large numbers of single trace operators in order to diagnose what's going on in this shadow region.
Okay.
And but then if I use those operators, those don't preserve the background in any sense, right? If I acted with those operators on the boundary, I would basically destroy the state that I have. So
this is where like, sorry, go on.
Well, I was just wondering whether there's some kind of like quantum non-demolition issue here that if my task is to measure what's going on in the region beyond the causal wedge using only light operators at low energy near the boundary, then I can't do it. And that if I really wanted to figure out what was going on there, I would need to use such a heavy operator at the boundary I'm no longer talking about the same space-time.
So, okay, so the point is that generically a heavy operator, you're right, will just destroy the space-time. But the point is that there should be very, very, very special, sorry, it's okay, there should be very special heavy operators, like combinations of heavy operators which do the job. Okay, an example here is that you can imagine that in this time band example. Okay, I am not drawing it, so let me just
Yeah, I
let me
understand.
not drawing. So you can take this operator and evolve it here, and this is clearly a bunch of light operators just smeared out over a large time, right? But then it becomes when you write it in terms of operators here, you have to use heavy operators in this region. But these are very special combinations which are actually light operators at some other time, right?
Right.
And so these special combinations do exist in a bunch of examples, and they will not. These special combinations won't destroy the spacetime, even though most heavy operators would. That's kind of the magic here.
Right. And
How do I know I have such an operator?
Right.
Right.
So
It sounds like you're saying that,
turns out
I have
that,
out of all the heavy operators I could imagine, there's some extremely small subset that don't destroy the space-time. But a priori, how do I know what that small, tiny subset of operators is?
So this set of operators, where you take,
if I took a generic heavy operator, it would totally destroy the space-time.
I agree. So if you take OA to be some nice light operator within A, and then you evolve it with the boundary reduced density matrix like this, it turns out that we can control these operators and they don't destroy the spacetime, and they are enough.
Okay.
So this is something that you can read about in this paper by Faulkner and Lukovic from 2017. They show how this is actually enough. And yeah, there's also some PEXMAP papers which in spirit are doing something very similar, but aren't quite the same.
Okay, thank you.
Yeah.
so, sorry, just so I understand that these OAs are operators which are heavy at, say, the point of insertion, but special in that after evolving for some time, they could become light operators at some later instant. Maybe.
Exactly, like they're sums and products of a lot of things, and some of those things in the sums and products are heavy at that time. But basically, like, yeah.
Okay. Okay. And then I'm sorry, just to maybe try to anticipate, perhaps wrongly, the rest of your talk. Are you saying that you're going to be using with your matter fields and the extra freedom that large but not too large central charge brings, you're going to be trying to construct some analog of these kind of operators which are tractable, which will allow you to see the peninsula region in some sense with backreaction?
Yeah, basically what I'm going to say is that you can take some of these light, there are like specific light operators, okay, the light and the simple in the causal wedge, but then their backreaction somehow, when you let them backreact, right? So you can control the operator itself, but you can't control the backreaction from the boundary. The backreaction is just gravity doing its magic, and then the point is that after backreaction, they no longer commute with these special heavy operators here. But before backreaction, they did at semi-classical level. And that's going to be the point of the talk, yeah. Yeah. And yeah, just to, because getting, yeah, I don't know how much I'll be able to get through. I'll just say that we have special operators here, which actually have non-zero commutators with all operators in the peninsula when the peninsula is small. And it's going to, that's the main, yeah. Cool. Sorry, yeah. Now, I just wanted to tell you that generically this causal wedge and this entanglement wedge are not the same, but in very specific cases when the state of the CFT vacuum and the the region A is a ball, which means its boundary is a sphere. The bulk is vacuum ADS, and the causal and entanglement wedges coincide. And one of the things is that there's a conformal symmetry which tells you that in this equation, in this case, both of these terms are separately zero. Okay. Yeah. So now this slide is a bit busy, but it's almost the entire point of the talk. So what we'll do is we'll take an excited state whose matrix differs from the vacuum at this order. This is the back reaction of a stress tensor of order C. Okay, and in some nice gauge. Okay, so let's just draw it out. So suppose there's some positive energy shock here, some positive energy here. The positive, okay, and this here is the causal surface. This is the entanglement wave, sorry, the HRT surface. Okay, and we are looking at just the two null directions transverse to this whole setup. Okay, and now the important the thing that will be at play. I'm going in a gauge where the unperturbed causal surface and the HRT surface are at x minus equals 0. Okay, I told you they coincide. Well, they coincide here in this picture. In the vacuum. Now we are exciting the state. So now the causal wedge is here, and the HRT surface is here, and we are interested in the minus null separation between the two surfaces. Okay. And now, how do you find that? Turns out that the ingredients are there. To find the RT surface, you just use the extremal surface equation I gave you. And it turns out, and there's some differential operator acting on this XRT minus, which is a bulk entanglement derivative plus some other stuff. Okay. And this is all at leading order in C.G. Newton, by the way. So there's all this stuff here. And the causal surface can be found by the following fact, that any null line from this point reaches exactly the tip of D of A, that one point there. So you integrate Einstein's equations backwards with that boundary condition. This is similar to how people find event horizons. Okay, and so you find that it's some differential operator acting on this XC minus. Okay. And the source is now the integral of stress, the energy flux passing through the future horizon. Now, what is the differential operator? I told you this is just a cross section, so it's a differential operator in the directions that I haven't drawn, and it's the same differential operator in both cases. Really comes down to this fact. Okay, both equations have the same differential operator, and now what do you say? Yeah, so, and one of them has a source which is an entanglement derivative, one of them has a source which is the energy passing through the future horizon. Okay, and the differential operator here is negative definite. There's a zero mode, but the boundary condition set the zero mode to 0. Good. Now for the consistency of entanglement wedge and causal wedge reconstruction, we know causal wedges can always be reconstructed. So it better be inside the entanglement wedge. Okay, that requires that this number be bigger than this number. Okay, which requires that this combination of bulk QFT quantities be positive. Is it positive? Yes. There's something called the quantum half average null energy condition, which is true for QFTs. And why is it called that? This is the half average null energy because averaging over half a null line, and this is what makes it quantum, the second term. Like the same way earlier we took an area and added a bulk entanglement to make it a quantum, a generalized entropy. This is like the first quantum correction to that. And this is not, sorry, one second, Shiraz, or whoever that was. This first term is not necessarily, just wait.
Okay, I'm sorry.
Yeah, this first term is not necessarily positive, but the combination is, and this will be crucial for us. can I restrict to like kind of semi-pressing or relevant questions from now on, because it's been 1.5 hours and I should let you guys go soon.
Okay,
I mean,
I will just
yeah.
take a minute if you don't mind.
Yeah, sure.
What we are trying to do is choosing some particular nice gauge and trying to find the entanglement wedge and the causal wedge for a generic peninsula region. And meaning, I'm sorry, we are trying to find the causal wedge and the entanglement wedge for some with some background bulk metric and small order G Newton effects in it. Is that what we are trying to do?
Yeah, basically the background bulk metric differs from the vacuum at order CG Newton, and so we can do perturbative expansions around the vacuum metric. And so, yeah.
Excuse me. So let me also suggest that we reserve our questions for the end. And if there are pressing questions, you may interrupt. Please go ahead.
Yeah, thank you. Now, good. So now we have this fact. So now we know that this difference here is given by this quantum half average null energy, or the Quane. It's called the Quane, and the condition is called the Quanec. Okay, you pretend the H is a U. And this D being negative definite is an invertible differential operator. So like, given this object, you can just calculate the null separation. Okay. And basically what we'll do is we'll construct states that saturate this inequality, and so the null separation will go to 0. It's that simple. And okay, good. There's one more example. So here A was a single ball. Basically the same thing works when A is, say, 2 balls, but they're not intersecting. Okay. But then you take this just a vacuum state in CFT. What happens is that in this case, the entanglement and causal wedges do not coincide because of bulk entanglement. Okay. The bulk entanglement between this causal wedge and that causal wedge is order C, and so that creates an order CG Newton contribution to the extremal surface equation, and so you have to go a little bit out. Okay, and that contribution again is like the same differential operator turns up for each side. Okay, so now I'm just looking at one side here, and there's a bulk entanglement derivative, and this bulk entanglement derivative is protected by something called the monotonicity of mutual information, which which actually we'll come to later anyway. Good. Like, sorry, it's this, the sign of this guy is protected by this monotonicity of mutual information, which is a fact about quantum mechanics, all quantum mechanics. Good. And more generally, you can take many regions, many ball regions, and an excited state side. Well, some of these ball regions can be an entire CFT, and like it could be a black hole. It could be close to a black hole state. Okay, in that CFT, that also works. And then the same equation from this equation, which tells you that the null separation in each component is given by the integral over the Quane at that boundary in that region. And it should be noted here that the right hand side is a one-dimensional integral. Okay, where did it go? Yeah. In doing the variations to find the extremal surface equations, we're doing a variation point by point. So you just end up with a one-dimensional integral over the future horizon. Okay, you don't, the transfer directions turn up only in this D operator. Okay, and so again, this is also positive because of the Ronak. Yeah. So now let's quickly go through the old examples. We spoke about seeing was a reconstructing. Seeing is just making sure that there exists a non-zero commutator. Reconstructing is actually writing down the operator. And there are examples where reconstructing it can be shown to be same as seeing from both past and future. But that's in flat space. But we will only talk about seeing today. We won't try to reconstruct. So let us, now there are two previously known examples and both of them use something called a shock. A shock is a localized pulse of energy, and we'll take shocks that live on null lines, they're null shocks. Okay, so suppose you have a Minkowski and you have a left moving shock, then the T++ of the shock is some energy into a delta of X plus. And how do you see the shock? You can calculate the integral of T++ across that shock. Okay, this is very confusing. So this took me the longest time to comprehend, but here X plus is increasing in this direction, but this is but then it's a left moving shock. Okay, but then to see the left moving shock, you have to integrate over the right moving direction. Okay, yeah, okay, good. And after backreaction, it causes a time delay which is proportional to the energy here. And how do you calculate the time delay? It turns out that at leading order, it's just the integral of H plus plus. And like really the visual similarity between these two equations is not an accident. It's like the entire machine for us. And the other important thing is that if you take a shock and you boost it, what is the boost? The boost is this guy. You know, you take X plus and you make it exponentially bigger, X minus and make it exponentially smaller. T++ has two indices, so you get a e power minus 4 pi. Basically, when you make X plus exponentially bigger, T++ becomes exponentially smaller by twice the amount. There's a 2 here, there's a 5. So the integral gets suppressed when you boost a shock. And I said this in ADS, in Minkowski, but the ADS story is basically the same. Okay, you have the same effect. While I talk about all this, well, there's the ADS Wedge example. So take your state to be a thermophile double, which we all know is which is dual to a maximally extended ADS short shell black hole. Okay, so that's this picture without the red line, so that the green lines actually go all the way here. And then just act on it with a positive energy creating unitary on the right. Okay, and then you evolve it backwards and forwards, so it has to come hit the boundary and then bounce off. Okay, so this is the full space time. Okay, and now you calculate the causal wedge. Well, in a null line from here comes, gets time delayed, and ends up at the tip. Right. Similarly, a null line from here comes, gets time delayed, and ends up here. So the position of this causal surface is alpha when t equals 0. Alpha is, I haven't defined alpha for you, just it's some alpha. Okay, and this little diamond here, which I don't know if you can see, my bad color choice, is the peninsula. It is what is not, okay, good, why is the peninsula? I should have told you. The U is a one-sided unitary. A one-sided unitary cannot change the entanglement. Right? It cannot change the entanglement between A and the CFT. It just, you know, and so the HRT surface is still here. Okay, earlier it was here, and now it's still here. Sorry, I'm rushing through this. So there's a gap, and this gap is the peninsula. And what happens is that if you just boost the shock up, because of that boost effect, the time delay gets reduced. And so now you can see that some of the peninsula is in the past of the right boundary. Similarly, you can boost it down and then it will be in the future of the right boundary. And by doing an infinite amount of taking this time here to be infinite, you can see the entire peninsula. Okay. So yeah, and there's it's exponential, like this thing, gap here, the minus gap goes reduces exponentially with S.
So, sorry, Ronak, what is your red line again?
Oh, it is the U shock. It's the positive energy shock.
Okay, the red
Yeah,
line is the U shock, and
yeah,
the green lines are just null geodesics as they pass through. Is that right?
yeah,
Okay.
exactly. Yeah,
Thank you.
yeah,
Thank you. Go ahead.
yeah.
Mhm.
I have used a consistent color scheme where green lines are like basically null lines emanating from the boundary region.
Okay.
So yeah, cool. So yeah, I should have said that earlier. Sorry. Mm-hmm. Now that is the first example. So this is a very simple way to see it. Like anyone with the knowledge of shock spacetimes would have guessed this. Other way, which is like extremely non-trivial, is called the Gauss-Jeffreys fault construction, and it says that you take the thermofield double, you act with an entangled unitary, and it opens up the wormhole. It lets you pass through the wormhole. Okay, and the way it does that is it throws in negative energy shots. Negative energy shots cause a time advance. So you can imagine that, like, yeah. So basically, a line from here will go hit a negative energy shock, end up out here. Okay, I'm imagining a negative energy shock here. Good. And yeah, it turns out that, like, in the example where A is the union of two balls, okay, where I said that there's a peninsula because of bulk entanglement derivatives only, the same idea works. You do an entangled unitary between the two balls, okay, and it throws in a negative energy shock, and so signal in the peninsula gets out into the causal diamond. Earlier it was a black hole, now it's a causal diamond. But the story is the same. It was pointed out in this paper, and that's how I ended up on this project at all. Good. And so just to review, these two examples were, wow, the first case was when the peninsula was sourced by energy. There's just pure energy. There's no entanglement. Okay. And how do you deal with it? You boost the energy to oblivion. You just keep on boosting till it doesn't do anything. And the second example was an entanglement source peninsula. Because you have entanglement, you can locally create negative energy. Okay. And this is where, sorry, in this Quanek, yes, in this Quanek I kept on talking about, this is where the fact that the first term is not positive definite came in. Because if the second term has the right sign, the first term can be negative. Okay, and the first term can be negative only to a bounded amount. That's what this Quanek is telling you. And like when there's entanglement between the two causal wedges.
Sorry to slow you down, Ronak, but just go back there to that Quanek allows for negative. So the point is that the Quanek does allow for negative energy, but the average has to be positive or whatever, right?
Yeah, right. It allows for negative energy, but it allows for a very a bounded amount of negative energy.
Right, right. And that bounded amount means that the wormhole opens up for some time in Gauss-Jeffreys balls, if I remember, right? And then it closes again.
Yeah, basically.
Okay.
That, yeah.
Okay. Right. Right.
So, right. Yeah. So that's how, and basically having non-trivial entanglement derivatives was crucial for this. Okay. So it turns out that there is a unitary operator that very generally does both of these at once, can be shown to exist in like algebraic Q of T. It's called the Cocycle flow, and I should tell you very quickly about it. So okay, there's some definitions. The reduced density matrix is the it's a partial trace over the full state. If you don't know what this means, it's okay. I won't use it. The modular Hamiltonian is basically minus of log of reduced density matrix. Okay, and the modular flow is the Heisenberg flow generated by this modular Hamiltonian. Okay, modular flow is good in the continuum. The other two things are divergent to the continuum. There's something called the split vacuum called S omega, which is basically when you have like A has many subregions, like it's a union of balls. You reduce it to each subregion and then take the tensor product and then purify it. You find some vector in the full Hilbert space of A union A prime whose reduced density matrix looks like that. Turns out these things exist. It's not unique, but they exist and they have finite energy. This is a pretty cool fact. Okay, so now the important entanglement quantities are entanglement entropy, which is just the expectation value of the modular Hamiltonian in the state of interest. So here psi, these two are the same index, psi and psi. The relative entropy can be thought of as the following. It can be thought of as the difference in the expectation value of the vacuum modular Hamiltonian. The second thing here is the vacuum minus the difference in the entanglements. What is the difference in it here? It means that you first evaluate it in psi and subtract out the value in omega. Similarly for the entanglement. So this is S in psi minus S in omega, and this is expectation value of k omega in psi minus expectation value of k omega in omega. This is called the relative entropy. The mutual information between two regions is the relative entropy between the vacuum and the split vacuum corresponding to those two regions. Okay, and so relative entropy and mutual information, as you guys might know, are UV finite. They exist in QFT. The paradigmatic modular Hamiltonian is when you have A, which is just half of space. Okay, yeah, and in that case, it's just a boost generator, which looks like this. This dy root h is an integral over the boundary of A, which is this point here. Okay, and this generates a boost about that codimension 2 surface. And this is true both in ADS and in QF in Minkowski. Just you have to be careful in ADS that you have to, the z direction has to always come out of the screen. For ADS, the radial direction. And if you just look at what the action of this full modular Hamiltonian is, it just boosts everything. It's an isometry of both spacetimes, so it does nothing basically. But Ka alone does something horrible. It like makes a kinky slice, and so it has an infinite. Ka alone, this is the reason it's bad. It's a bad operator, and this guy has an infinite energy. Okay. This was a small detour where, because we have this, we can actually take derivatives of circle.
Sorry to slow you down, Ronak. Please excuse me. Just go back to the previous. What is Ka and Ka prime? No, not that one. The next slide.
Oh, good. So Ka and Ka prime are the. If you notice, the modular Hamiltonian had two indices: the state and the region. I suppressed the state index, but the region index is A and A prime. A and A prime are the two regions. Like right is A, left is A prime.
Oh, I see. Okay.
Yeah, sorry.
No.
Yeah.
Thank you.
Yeah, good. And basically, that's the reason that it's an integral over the entire horizon, like not just one half of it.
I see. I got it.
Ka alone, Ka alone is the integral over like the right half of the horizon, but then there are some scheme-dependent constants you have to add. It's a bad operator.
And I guess the point is that K minus K prime doesn't have the divergences of K, right? So
exactly.
Okay, got it.
Yeah. Great. Sure, thanks. Okay. Now you can use the expression in the previous slide to get basically, using this expression and the fact that relative entropies are monotonic, which means that relative entropy for a smaller region is smaller. Okay, because relative entropy is a measure of distinguishability. If you lose some operator, things should get less distinguishable, not more. Right? So if you just take, so now you can just, right, so relative entropy has two terms. Right? One is this k omega A, one is the entanglement term. And so you can just try to infinitesimally reduce the region here, right? And this, the effect of this can be seen by doing a delta by delta x plus, the same sort of wiggle that we've been talking about. And the delta by delta x plus acts on this term, okay? This x plus there. And what you find is that monodicity of relative entropy tells you that this guy is positive. this is the relative entropy between a state psi and the vacuum state omega. And use these deltas again to remind you, are you evaluate it in psi and you evaluate it in omega psi. The deltas are where you evaluate it in psi and then in omega and subtract. Again, this vacuum subtraction is essential. It makes sure that this is a UV finite operator and not scheme dependent. And yeah, earlier we saw exactly this combination turn up without the deltas. The reason the deltas weren't there was that I lied. Those deltas were there. I just suppressed them. Good. So you can see that the same combination, this combination, which it sources the gap between the RT surface and the causal surface. Okay. Good. So now I won't go through this slide. It's a bit of intuition, but the final answer is, final point is that this object, the Cocycle flow, which is written as d omega d psi a s. This is called the base state. This is called the state of interest. This is the algebra, and this s is a parameter. It's defined as defined as a difference of flows between the two modular Hamiltonians of psi and omega. You do modular flow. You do this modular flow with psi, but then this operator on its own is bad. It's not UV finite. But then, so you subtract out the modular flow of omega, okay, and this kind of restores the UV structure of the state. So this guy here is a UV finite operator. It exists within QFT, and it lives within A. It's an operator in A.
Okay. Ronak, I'm really sorry. I know you're out of time, but just if it doesn't delay you too much, although you explained it, what is the state dependence on the modular flow operator? I didn't understand, because I always think of Rindler space. And does it mean because you trace out on the other half or something? I mean, how is the state dependence arising?
Oh, good. So the modular Hamiltonian.
I got it. Thank you. Yeah. Okay, go ahead.
Yeah.
Good enough. Go ahead.
So good. This was actually a good point. Suppressing the state here was the worst idea idea ever. Let me just make it clear, Soni, sorry. Is that this is both k omega A. So this boost action is only for the vacuum. It is not true for any other state. Okay. And so like in general, k psi for a general state, k psi, the k psi operator is very complicated. But for the vacuum, we know it, and we can do a lot of things just by knowing this one thing. Okay. Like I just proved an energy condition for you. Cool. And this Cocycle flow is like this. It's like the difference of the two modular flows.
I see.
Okay. It modular flows all the interesting part of psi, but leaves the UV structure intact.
I see.
Good. And Cocycle flow you can show using a two-line calculation, which I will not go through. Is that basically if you take an operator A in A, OA, and evaluate its expectation value in the state psi s, where psi s is defined by the Cocycle flow acting on psi. Okay. Notice this is a completely right-sided operator here. Okay, so the reduced density matrix on A prime is the same in psi s and psi. Okay. It looks like yeah. So anyway, you can prove that the matrix, the expectation value in the psi s state is the same as the expectation value of the modular flow operator. Like the operator modular flow is vacuum modular flow. Okay. And we know vacuum modular flow. It's a boost. It's just boosting OA. Okay. We've seen there's a very nice operator. It's called the half average null energy. It's the integral of the stress tensor over the future horizon. And when it gets boosted, it gets exponentially suppressed. And this effect is how we dealt with energy source peninsula. And this is the reason Cocycle flow would work in a case like that.
Okay, I'm really sorry, but this slide seems really crucial, and I'm sorry I haven't understood it. So I'm going to slow you down. Now, so psi is some general state, right? Complicated state. and therefore Ka psi s is some terribly complicated operator in general.
Yeah.
How did you finally take OA in the psi s state and just write it in terms of the modular flow in the vacuum? What
Good.
was missed
So
that?
the trick, okay, the trick is the following, that Ka for any state, this is true. Okay, this is just a fact about states and modular Hamiltonians, that if you act with Ka, you can just might as well act with Ka prime. Okay, because it's the same reason that in the vacuum case, Ka minus Ka prime was a boost, it did nothing.
Right.
To the state.
I understand.
It was an isometry, yeah. So this is a complicated non-local symmetry of the state.
Okay.
Okay. So what you do is you take this guy on the right, convert it to an Ka prime.
Okay.
And now when you conjugate, the Ka primes just go through the O and annihilate each other. Yeah.
Okay.
Yeah. Sorry, I was skipping that derivation,
No,
but
good,
it's
good.
really that simple.
And so you just have the modular. Okay, got it. Go ahead. Yeah, I'm with you.
Yeah. Awesome. Now this is a second crucial fact about Cocycle states. Sehan and Faulkner in this like powerhouse of a paper proved that in this state, in this these should be psi s's here. I'm going to draw an S. In the float state, the relative entropy is second differentiable at the origin. Why is this? Normally, like we don't think about this very much, but this is non-trivial because we know that everything on the right is getting boosted and everything on the left is completely untouched. So it looks very discontinuous. But these guys using AQFT techniques proved this. And this, I should also say that AQFT technique, this is the sort of thing where AQFT techniques are basically indispensable. It would be significantly harder to prove it without that. Okay. And anyway, and not only is it non-trivial at the level of heuristics, which I just gave you, it's also non-trivial at the level of equations. You just plug in what this is and what this is into this equation. Okay. And what you find is, these equations. Let's focus on the top one. So minus delta and delta is some very small number, which I'm integrating around x plus equals 0 because there's a shock at x plus equals 0. The left moving shock. Okay. The shock has magnitude e power minus 2 pi s minus 1 into the mod of the entanglement derivative. This is a negative number. There's a negative energy shock in this state. Okay. And this negative energy shock, well, that is exactly what GJW did for you. This is what Gauss-Jacobs world did. It's how we dealt with entanglement source peninsula. Yeah. And yeah, so that is the two facts about Cocycle flow states. And yeah, good. So there are generalizations. So this works even if A is a ball. So I mentioned where A is a Rindler space because I was using boosts. But in CFT, Rindler spaces and balls are the same. Causal dimensions of balls are the same up to a conformal transformation. It works in ADS Rindler. Okay, ADS Rindler is like Rindler, but it's an ADS. It's the same picture, but sorry, it's going the wrong way. It's the same picture as the Rindler space picture, but the radial direction is outside the page. Okay, and again, there's the same symmetry, the boost symmetry, which allows you to do this. Okay, and in the split case, okay, where the Cocycle flow looks like this, and each of these is a local operator. Okay, it's just an integral. It's a separate boost in each region. So you can deal with it separate. You can deal with it equally easily, and the equations from before are true in each of the regions separately. Okay, there are shocks at the edge of each region. Cool. So now I have given you. I will in all the ingredients of this. Let's quickly show you what's happening. So couple of sections ago, I explained to you that the null separation between the RT surface and the causal surface is sourced by the Squane QHNE object, okay, in that state, okay. CC floor states, I didn't say it in the, there are two facts about CC floor states. First fact is that the energy leaving the future horizon gets boosted. Okay, I've written it in a funny way. This t plus plus 0 actually cancels the 1 here. So this is the equation you already saw. And at the boundary, there is this shock. Okay, we add them up and we see, I missed a minus sign, but when you add, there's a minus sign here, which I missed. This guy is a negative object. So anyway, when you add them up, you find an object we've seen before is the Quane. Okay, it's the quantum half-ordered null energy. And well, all the ones and so on cancel with each other, and you find this, that the Quane in the float state divided by the Quane in the unfloat state is e power minus 2 pi s. Okay, and this is true in ADS as well. So it exponentially suppresses this Quane object. So this Quane object was the source for this differential equation. This D here is an invertible operator. So when this goes to 0, so does this, and it's monotonic. This is a positive definite differential operator. Okay, and yeah, just to remind you of the full setup, we are looking at states where the difference between the RT and the causal surface is order CG Newton because of either a bulk metric difference or bulk entanglement. The unitary of interest is the following: you do Cocycle flow in the region in the causal wedge, where the base state is the one in which causal and entanglement wedge coincide, which is either the vacuum or the split vacuum, depending on how many components you have. Okay, this is a bulk Cocycle flow. So it's within the causal wedge, and it's a unitary that's within the causal wedge algebra. It's a finite energy unitary, so its energy does not scale with G Newton. So you can HKLL reconstruct it. Okay, and when you do this, you find that the null separation reduces exponentially. So you can see more and more of the peninsula. And if you want to this thing, and just to do some order counting, this guy here is CG Newton. Okay, so if you want to make this G Newton, when it is right, G Newton is like it's like a resolution. We can't go beyond G Newton. We just need S equals log C, which is not too big. It does not scale with G Newton. And so, yeah, so now we've been to the accuracy we're working at, we've seen the entire peninsula.
So, sorry, Ronak, again, I don't want to slow you down, excuse me, but I thought, when you gave the introduction to your talk, that what you were going to show is that backreaction would make the causal wedge fluctuate into the peninsular region. And
yes.
Some calculation as any relativity person does of computing the backreaction, etc. Now you got this cons whatever flow, which you're using. And one question I have is the modular Hamiltonian or whatever that is generating your CC flow made out of, simple single trace operators, to go back to some of the discussion we were having, or does it involve very complicated operators? I mean, the question we were asking was, can you see the peninsula out of relatively simple operators, right? And if so, how? Given that the causal wedge doesn't extend there. So I'm a little confused, but you can come back at the end.
No, actually, this is basically the end of the talk, so it's a good time to answer that question. Okay. The answer is yes, it is. So the point is causal wedge Cocycle flow, and Cocycle flow, even though the definition is complicated, in practice, if you try to write it down in terms of operators, I mean, it's going to be complicated, but it's not going to be G Newton complicated. Whereas other things are G Newton complicated, like the complicated of the order of n squared. Okay, In particular, we can take, there are specific examples in 2D where we can take free fermions, okay?
Yeah.
And do this sort of split vacuum thing where the state is a vacuum, but you have two regions. And then we can do the entire calculation completely explicitly. We know the Cocycle flow for the, basically in free fermions, we know the modular Hamiltonian for two regions as well. Okay, and so you can actually calculate write down the Cocycle flow operator, just written in terms of bulk free fermions, and you can calculate the energy distribution, you can calculate everything.
Mm-hmm.
Yeah, and another,
so
just one, Sandeep, yeah, just to finish answering Sandeep's question, sorry, is that the place where we did the relativity calculation was that we took as input this guy, and we calculated this. This is the relativity part. This is the part where you're calculating backreaction. You know, letting this thing depend on the energy distribution is the backreaction calculation, right? So you're using Einstein equations here.
Mm-hmm. Mm-hmm.
Yeah.
Okay. Yeah. I think Emil might be asking this. So
Yeah.
but let me just pose it, but then I'll wait, let Emil ask his question, which was, you know, as Emil was saying, the general thinking might be that you need some very complicated operators to probe the inner region, the peninsula region. Are you saying because you have this intermediate window of bulk matter with C, which is large but not very large, you are illustrating how operators involving the C number of bulk fields, because of backreaction, do allow you then using simple gravitons, etc., once the backreaction is taken into account, to see the peninsula? Might illustrate how more generally for very heavy operators, the backreaction in a sense allows the geometry to fluctuate and go into the peninsula. Is that the
No,
let me stop and then you should ask. Sorry.
So yeah, good. So that's right actually. So the first thing you said is right, which is that these operators, though they look complicated, are still complicated at the order of C, not at the order of 1 by n squared.
Mm-hmm.
And the backreaction is easy enough to calculate. It's just Einstein equations linearized. Mm-hmm. And it somehow does as well as it can. It cannot go beyond this. Okay, because it really goes and hits the entire, like it goes and hits the boundary of the entanglement bridge. Okay. So it's like it's a maximal case, but in a perturbative thing. But it is kind of a, so in earlier entanglement wedge calculation discussions, you explicitly needed the boundary density matrix. Mm-hmm. And the boundary density matrix is believed to be exponentially more complicated than the bulk density matrix. Okay, there's this paper by Adam Booland and Umesh Vajradani from last year, which has some evidence for this, and also this paper called the Python's Lunch. And so somehow, yes. So at least in this case, we can do it not in complexity e power 1 by g, but just gn power 0. And that is the advantage. But the trade-off is we can only do perturbative cases, whereas other people can do everything. Yeah. Yeah. Sorry, Emil, did you have a question?
Yeah. So I'm trying to understand where the heavy lifting is being done here. So, I mean, the way you construct these operators is to act with the modular Hamiltonian, but the modular Hamiltonian knows about the state. Mm-hmm. And so, but if I know the state, then I know what's in the peninsula. So
no, you know the state only in the. So okay, good. What do you need to know to create this Cocycle flow? All you need to know is expectation values of operators in the causal wedge. From there, like you do not need to know anything about what's happening in the peninsula. Like you just need all expectation values in the causal wedge. And this is like, you know, this gives you the reduced density matrix, which gives you the Cocycle flow. So in this sense,
now you've confused me, because aren't there plenty of states in the theory that have different field excitations in the peninsula, but the same stuff going on in the causal wedge?
Yes.
So that data is in the state, right? It's not
It's in the boundary
in the
state.
causal wedge.
It's in the boundary state. Okay. It's not in the, we are looking at states reduced to the causal wedge, right? We are looking at states restricted
Sure, but
to causal wedge.
it's the full theory, not just the single trace operators, not just the simple operators.
No,
right?
no.
You need to know the state.
It's within the bulk effective theory. It's roughly speaking just the single trace operators, or like the order one trace operators, not order n squared trace. So it's really within effective theory. So it's within the, yeah. But the knowledge of the peninsula is actually there in these order n squared operators, which which somehow is not there in our effective theory because of
But so I guess I'm still confused. The modular Hamiltonian you're flowing with is the modular Hamiltonian of the full theory, is it not?
No, it's the modular Hamiltonian of the bulk effective theory, bulk effective QFT. Okay, good. Sorry, I should have been clearer about this. So what we are doing is we're taking the bulk effective QFT. Okay, it has some quantum state. We are reducing it to the causal wedge. Okay, in both for psi and omega, and we're using that modular Hamiltonian. So it it does not know about what's happening in the peninsula. Yeah.
Okay, but then I'm get back to my previous confusion, which is that let me construct two states, which one of which has qubit excited in the peninsula, and one which doesn't, and which has the same set of excitations of bulk fields in the causal wedge. So how does your construction detect whether the qubit in the island, in the peninsula, is excited or not?
So the point is that this is where it's crucial. It's a seeing procedure, not a reconstruction procedure. So I was just So suppose you have a qubit excited here. Okay. What happens is that after doing this, actually, maybe can I just introduce this picture before answering the question, if you don't mind? Yeah.
Sure.
So this is like a heuristic picture of everything that's happening. Okay. This is a perturbative state. The green lines are the causal wedge with this energy background. There's some energy going around here. Okay. This light green line is the unperturbed causal wedge, is the causal wedge in the vacuum. And this blue line is the entanglement wedge. And basically the entanglement wedge is bigger than the unperturbed causal wedge because of these two spins which are entangled. Okay, and the causal wedge is smaller than the unperturbed causal wedge because of the energy which is going out. And then when you do CC flow, basically what happens is that the energy going out gets boosted off. So the future horizon of the causal wedge goes to the unperturbed value. But then it can't go beyond the unperturbed value, right? It gets stuck there, which is where the shocks come in, and the shocks make sure that this is a negative energy shock, and they make sure that anything in the peninsula gets out. Okay, so now this is like what we've done. Now to answer Emil's question, how do you tell whether there is an exciting? So suppose you have a excitation here. I want to tell whether it's there or not. Well, how are you going to detect it? You're going to detect it. So call this operator phi and call some operator here O. You're going to detect it by measuring the following commutator. O phi in the full state psi s. So now here it is crucial that you have the boundary state, right? Okay, so this is a boundary state. So but we already, by assumption, we have, what do you say, we have expectation values in the boundary state. You just do bulk effective theory and you get the answer. So the information, what CC2 is giving you is it's giving you a kind of causal relationship, a semi-classical relationship between this operator and this operator, this phi operator and this O operator. But then the actual information about what the phi field is doing is there in the state in which you take the expectation value. So this is how it always works, like in causal relationships. Like a null line, like a causal relationship gives you a relationship, a non-zero commutator, but the actual information transmission you can only see when you take the expectation value in a specific state. And this is the same story. But taking the expectation value here is simple because you just do bulk effective theory. You don't have to do anything complicated. And that is the answer, I think. Does that make you happy?
So, sorry, Ronak, just one quick clarification. In this diagram, where are the order C bulk fields? What are they? Are they the shock waves in green? What are they? Are they the operators?
There's the little arrows. There's a little arrow which are entangled.
That's what I thought. They're the qubits. Yeah. So, but their back reaction is what is causing the causal wedge to fluctuate all the way to the entanglement wedge, no?
Mm-hmm. Yeah.
Okay, now that wasn't quite how your heuristic description here went, or I misunderstood maybe. Anyway.
Oh, no, like, okay. So, when I say, okay, what are time delays and time advances? Maybe I was unclear about this, I guess. Time delays and time advances are what happens when you let a stress and a null stress energy back react. So when we talk about time delays and time advances, that is back reaction. Right? And so what's happening here is that when you reduce the when you boost this energy off, okay, this is a new QFT state and it has a new stress tensor distribution. And when you let that new stress tensor distribution back react, there's no time advance due to this energy, right? And similarly, in this new state, there are some shocks here, and the back reaction of that negative energy shock is what is the time advance.
And those shocks are originating because of your qubits?
Yeah, they're originating because CC flow naturally gives you these shocks. These qubits are supposed to symbolize that when you move. These qubits are supposed to symbolize that basically, you know, when you take this region, this qubit, this entanglement is not there, so the entanglement actually changes with when you wiggle the region. That's sorry.
So is it fair to say, so if I think about something like Casimir energy, right? Mm-hmm. That's a negative energy associated with a region of space, and it's governed, and it sort of, in terms of how big it is, it's governed by C. So, is it fair to say that the region of the size of this peninsula region that you sort of can make accessible is a region whose size is governed by C because the vacuum entanglement of the quantum fields is governed by C? And G Newton is not coming into it because G Newton governs the size of something else.
No, it's the size here is CG Newton.
CG Newton.
Because because like everything, the gap is created by back reaction of order C star.
Okay, so right. So I see. So you say the negative energy I can make available is governed by C, and then the back reaction of that on the space-time is governed by G Newton.
Yeah.
Okay.
That's right.
That's right. Yeah.
Just could I ask? I mean, are you done, Ronak? Shall we clap and continue?
1 second. Let me just see what's there. I had one more. I had a conclusion slide. In fact, this is getting to what Emil was asking, you can use a complicated entanglement to write simple bulk books. Yeah. Yeah. So this perturbatively small is the fact that it's, the peninsula has to be CG Newton. So you can reveal a CG Newton size region. And yeah, the back reaction is the fact that the time delays and time advances are changing. So that's where it comes in. Yeah. So this is the conclusion. I have a slide about a project that's ongoing, which is vaguely related. If you guys want to hear about it, but if you don't, it's okay.
Okay, maybe I can suggest we can all clap.
I can tell later because everyone's been here for 2.5 hours.
Sorry about this.
Very good.
Yeah. Thank you.
Okay. Any sort of any questions?
So
Ronak, I'm going to ask you offline some follow-ups. Okay, but
Yeah, sure.
Yeah, thank you.
Gautam, you had a question?
Yeah, so I just wanted to say that you have some example worked out using free fermions. Is that right? So
Yeah.
is this already available or you're writing it up?
We are like finishing it up. It should be out next week.
Okay.
Yeah. The free fermion thing is there's this very nice paper from November or December by this guy called Yiming Chen. Okay. Where like he explains the free fermion. Basically, what happens is that free fermions have a special property that in 2D, we know the modular flow of this region. Free fermions and chiral bosons are the only two theories for which we know, thanks to Cassini and Huerta. And you can basically use that to, the modular flow of two regions. You need to know the modular flow of each one separately because it's a CFT. And so you can actually do calculations.
I see.
Yeah, and Yiming Chen explains the whole thing very nicely.
Yeah, maybe I'll ask you about the reference later on.
Yeah, sure.
Thanks.
Okay. Hey, Ronak, I had a quick, just a basic, I just want to ask, re-ask Emil's question just to make sure I understand. What I understood was that if I've given, you give me some state on the boundary, and at the beginning of the talk, we agreed, I thought, that if you give me just 1-point functions of single operators, simple operators, single trace operators in that state, that is not enough to reconstruct what's happening in the peninsula. There could be two different states in the peninsula, which is consistent with the same 1-point functions.
Yeah.
I thought in the answer to Emil's question, you were saying that in the end, you were using 1-point functions of simple operators to distinguish. I couldn't understand how this both. I mean, however you did it.
Yeah.
I couldn't understand how mutually consistent.
So good. There is a sense in which 1-point functions of single trace operators sorry. Well, 1-point functions of single trace operators are not enough. That is right. But what you can do is that you can play around with 1-point. Okay, first of all, it's not just 1-point functions. Let's just say C-point functions. Would you be happy with that?
Okay.
1-point functions are enough for me. Huh?
Okay, good. That would help me, I think.
Yeah. So let's say C-point functions. So what you can do
C-point
is that
you can points. This is different from 1-point functions of multi-trace operators, or is it is it the same as 1-point functions of multi-trace operators?
So good. If you have like C-point functions of single trace operators, you can take coincident limits and do this sort of renormalization stuff to get and then like figure out the OP, and you can get like combinations of multi-trace 1-point functions. Right?
So do I understand right that you're saying that classically 1-point functions of multi-trace operators would just be the products of the 1-point functions of the single trace operators, but all your information comes from the difference between that expectation and the actual answer. Is this right?
Yeah, sure. I think I will cautiously say that yes, but I would need to think about the language.
I see. Okay, but please complete what you were saying. I interrupted you.
Yeah. Now I was just saying that suppose you have single trace operators, you cannot reconstruct what's happening deep inside, but what you can do is you can muck about with the state so that the so there's a commutators between what's deep inside and like and like some simple operator, some simple single trace operator becomes non-zero at leading order. It was always non-zero. It was always 1 by n. But there are ways to muck about with the state just using simple operators and backreaction. So backreaction is where things get complicated because we don't know the boundary representation of backreaction. Okay, but we know the bulk understanding of backreaction. But backreaction is somehow taking these like C-point operators and mucking them about into like more complicated operators to allow these commutators to get enhanced.
You know, this language confuses me. I thought the whole point of general relativity was that if you've got some causal region, it doesn't matter what's happening for the backreaction outside that causal region. For instance, when we're studying black hole physics, once you've established there's an event horizon, it doesn't matter what's happening on the other side. Anything could happen on the other side.
Yeah.
Right. So since we're talking about causality, I would have imagined that something behind there, no matter how much it backreacts, cannot be accessed.
So this is the point, and nothing in the peninsula is touched. It's just that we can, what do you say? We can see it. Like the peninsula region is just completely untouched.
You know, one way in which something like this could happen is if there's a constraint equation.
Yes.
A constraint equation tells you that what's happening here is constraint related to stuff that's acausal, that maybe at least look. Is a constraint equation playing an important role in what you're doing? Is the gravitational constraint equation playing an important role?
Well, let's see. The gravitational.
That's what's governing the time advances. That's what's
exactly
the time advances.
So I you said, Emil, could you repeat that?
That's what's making the time advances and delays.
Right. Like you can do this in 2D where everything is constant.
Yeah. So for instance, just in an ordinary quantum field theory, you can measure the electric field far away and conclude from there that there has to be a charge somewhere, even though that place is space-like related to the where you're measuring the electric field. Okay? And that comes from a constraint equation, and that's not extremely surprising. Is that somehow at the heart of what's going on here or not?
Yeah, I guess, yeah. You're basically saying that look, you have a boundary region and you have a charge somewhere deep inside, and an operator of the boundary region and the charge somewhere deep inside commute. Okay, but what you do is you act with the integral of the electric field flux. Okay, you look at the state e power I electric field flux on the boundary acting on the vacuum. Okay, and now basically the expectation value of a boundary operator becomes sensitive to the electric field flux in this new state. Okay, so in this sense you're able to
Yes, exactly. You're able to measure something far away and yet conclude something about something space-like related because of a constraint.
Yeah.
And is that somehow playing a crucial role in your construction?
Yeah, exactly. Yeah, sure. Yeah, that's what backreaction is like. Like you can, the essential story is 2D, and in 2D backreaction is just constraints. There's nothing else.
Okay.
But it sounds like there's an opportunity for making some kind of Maxwell demon here, right? So you know, you can create little pockets of negative energy. You're saying, oh, I can use that to snatch something from behind the horizon if it's sufficiently close to the horizon. And so, but you're saying there's like a bound on that that's I can keep borrowing energy to do that, but eventually I have to pay a big price.
Yeah, basically like you, that's right. Because there's only so much negative energy you can throw in, where this Quantic like really tells you that there's only so much you can throw in, so you can only get so much out. And in fact, in like a 2D JT example where we can calculate things explicitly beyond leading order, what we find is exactly what you said, Emil, that like after enough flow, actually the what happened? Well, actually, I should tell you exactly how it happens. So the thing I kind of papered over is the second equation here. There's a right moving shock. There's a left moving shock which is negative, but there's a right moving shock which is positive and increasing exponentially. Okay, and that also backreacts on the signal. And beyond a point, the backreaction of the right moving shock completely closes up the peninsula. And this is the kind of the thing you were just mentioning.
Okay.
Yeah.
More questions? Okay, if not, maybe we can thank Ronak for a marathon and valiant effort. Okay.
It's not a TIFR talk unless it's 3 hours long.
Okay. So thank you very much.
Yes, thank you. It was a pleasure. Thanks a lot.